Thanks, Antonio. Thank you for the invitation and organizers, Gennady and Thibault and Aga, and so of course, Antonio. So I'm really happy to be here. You're going to see maybe later on, I'm especially happy to be here for some reason. But anyway, this is a talk about the Benjamin-Ono equation and its behavior in the small dispersion limit. And it's joint work with Elliot Blackstone, who's a postdoc at Michigan, Louise Gassot from Rennes, Patrick Gerard from Seclay, and my former PhD student, Matt Mitchell, who's now on his way to Orlando for a postdoc. Okay, so the Benjamin-Ono equation is a model for internal waves in fluids. And the idea is that a fluid in nature can be stratified into a less dense layer that's floating on top of a more dense layer. And in some situations, the transition between those two fluid density layers is a rather sharp interface that's called the pycnocline. It's a free surface and it moves around as the fluid layers are disturbed and so on. And so we may try to model the motions of that fluid interface. And that's what we mean by an internal wave, some kind of a motion of that free surface. So anyway, the Benjamin-Ono equation is an asymptotic model that's derived. It's kind of long wave and deeply nonlinear limit for one-dimensional waves that are propagating over a very, very deep lower layer. And it looks like this. So you have some kind of Berger's type terms over here, and then there's a small dispersion parameter times a non-local term, which is the Hilbert transform here in this kind of physics notation. Acting on the second derivative of the field with respect to x. Okay, so that's the Benjamin-Ono equation. It was derived in 1967 by Benjamin. Okay, so I would like to consider this parameter epsilon being small in the talk. That's the small dispersion limit. When it's very small, we might think that we could, in fact, drop this dispersive term epsilon hxx, uxx. And consequently, if we fix initial data that's independent of epsilon, it should really evolve in time approximately according to the epsilon equals 0 equation, which is written here with a superscript b for Berger's, okay? And the thing that we know, of course, about that equation is that it forms shocks in finite time for smooth initial data. And so, you know, actually, if you use the method of characteristics to solve the problem mathematically, you reduce the whole thing to solving some implicit equation, right? Solve the characteristics problem, and you're solving an implicit equation. And what really happens is that the number of solutions of that equation changes as time and space vary. And that's sort of the problem, right? I mean, we don't have a well-defined solution, and we try to insert a shock wave or something like that. So the picture you kind of generate from some initial data, I think here there was a positive bump and a negative bump, is something like this, where there's basically a unique solution from that implicit function problem outside of this kind of star-shaped region. And then there's some folds that happen where, in this case, there are 3 solutions where you see j equals 1 over here. And then there's this wedge in between j equals 2. There are 5 solutions there. And so here's like a cross section of this picture here. And you see sort of the shape of this multi-valued graph, right? Which we have to throw away because it's a physical problem and we can't use many answers. Okay. Anyway, I do have a message for you, which is that all of these different branches that you see in the picture are important when we consider the Benjamin-Ono equation. Actually, we have to account for all of them, and hopefully we'll see later on where that shows up. But for now, this is kind of the picture to have in mind. Okay. Right. So the thing is that there's usually a kind of shock that happens down here. This is maybe the earliest time. This is the gradient catastrophe point. And from there, you have to figure out what to do really with the Benjamin-Ono equation. Okay, so yeah, so we call that point XCTC, the critical point. It's down here in the picture, and what happens there is that the Berger's solution forms a negative infinite gradient. Right? So it's a gradient catastrophe. Okay, so anyway, so if we think about just the Berger's equation, if we consider adding some dispersive terms, like maybe the Benjamin-Ono terms. Well, if T is bigger than TC, then locally we know from the experts in the room here that there are 2 curves. There's an x minus of T and an x plus of T that bifurcate from this point. So some curve like this and another curve over here like this. Okay, and between those 2 curves, there's some dispersive shock wave, right? That's what we know. So that's the interval x minus to x plus of T. All right, so it's of some interest in general to determine how a given dispersive regularization behaves near that gradient catastrophe point and also near these curves x plus and x minus that come out of it, okay? So for the rest of the talk, what I would like to do is compare for you the behavior for two different dispersive regularizations of that inviscid Burgers equation. So one will be the KdV equation that's written here. This is the dispersive correction term for KdV. It's epsilon squared times 3 derivatives. And then here, of course, is the Benjamin-Ono non-local dispersive correction term. Okay, so so the thing is that for this problem here, the behavior of the solution of KdV close to that catastrophe point and the two curves x plus and x minus, that's something that was worked out in detail by Tamara Grava and Tom Kleiss about 15 years ago. And as usual, I'm like 15 years behind. So now I'm going to tell you some of the other answers. Okay, so anyway, so first let's discuss the curves x plus and minus themselves. So for KdV, you can find them, using this shock fitting technique that we heard about, or you can think about the degeneration locus for the 3x3 hyperbolic Woodham system for the KdV equation. But that's what defines these curves of x plus and x minus of t in the KdV case. But anyway, for the Benjamin-Ono problem, they're not the same curves. They're actually these caustic curves of the inviscid Burgers solution. So again, in this picture, they're exactly the place where you have a bifurcation in the number of branches of the solution of the inviscid problem if you continue it by the method of characteristics. Okay, so that's what these curves are for BO. Okay, different curves. All right, so let's now think about the left edge. So that's x minus of t. And for both KdV and Benjamin-Ono, the left edge corresponds to the place where the amplitude of the dispersive shock wave goes down to 0. Sometimes it's called the harmonic limit. But anyway, we'll call it the dispersive edge in this talk. So for KdV, what happens is that the amplitude of the oscillations of the dispersive shock wave decays down to 0 near that left edge, like the x minus of t to the 1/2 power square root is how the amplitude goes down. But for Benjamin-Ono, it's a little bit bigger. The dispersive shock wave gets bigger faster, I guess. So there's an x minus of t to the 1/4 power. It's a different kind of behavior of the dispersive shock wave. But we may ask the question, how does the dispersive solution look actually close to this boundary curve? That's the question I'd like to address. Okay, so to answer the question in the KdV case, we have to talk about first a nonlinear special function. And so this is the homogeneous second Painlev equation here. It looks like the Airy equation plus a cubic term, okay? And what we need is a special solution of that equation. It's called the Hastings-McLeod solution. And it's the unique solution of this equation that actually behaves like the Airy function with a multiplier of 1 here as x goes to plus infinity. If you change that 1 to anything else, it's a different solution that has completely different behavior in the opposite direction. But here we need the coefficient to be 1, and that's what distinguishes the Hastings-McLeod solution. And in the opposite direction, it's been shown to satisfy this kind of square root asymptotic behavior like that. So this kind of connection between the x goes to plus and minus infinity for the same solution of this nonlinear equation is an example of what's called a connection formula. So now we know how the Hastings-McLeod solution looks in two directions: very fast decay to the right, square root behavior to the left. Okay, so what's going on at the dispersive edge for KdV is that the elliptic functions that model that dispersive shock wave, they degenerate in a trigonometric degeneration to just, trig functions, cosines, okay? So the elliptic parameter m goes to 0. And so let's set u minus of t to be the Burgers solution continued from the left. So that's a well-defined value coming from the inviscid Burgers equation. And we'll let u denote the solution of KdV with initial data u0. And then here's the result of Kleiss and Grava from 15 years ago. So we fix a t bigger than the critical time. So there are some positive functions k and w of t and a phase, a real valued phase theta naught, so that the solution of KdV looks like the Burgers solution from the left minus, some number times epsilon to the 1/3. And then here's the Hastings-McLeod solution as a function of a variable capital X times a cosine with a fast phase and a slower correction plus error terms, okay? Now, this is as epsilon goes to 0. The x here is a rescaled coordinate near the edge by epsilon to the power 2/3. It describes kind of the width of that zone, okay? So we may say, looking at this result, that the amplitude profile for the KdV equation at the dispersive edge is governed by this function QHM, this Hastings-McLeod solution of the second Painlev equation. That's a universal result. You see the U naught does not figure in at all to the definition of this function. Okay, so that's why it's a universality result. Okay, so that's for KdV. Now, here's the corresponding result for Benjamin-Ono. So the dispersive edge is a different curve, as we said, but we can still define the Burger's solution continued from the left as a U minus of T function. And now we'll denote U to be the solution of the Benjamin-Ono equation with a rational function as the initial beta. Okay, so U naught will be a rational function. So then here's the result. So we fix a time bigger than the critical time. There's a positive function W and gamma, and there's a real value function beta and a fast phase theta naught. So that the solution of Benjamin-Ono is again the Burger solution continued from the left plus epsilon to the power 1/6 times this thing. So here's a phase, a real part of a phase factor with a fast part, a slower correction. And then here's an amplitude part. It's the 1 over the Airy function of e to the minus I pi over 3 times x plus an error term. And here, again, we're looking at some capital X as a scaled coordinate near the dispersive edge by epsilon to the power 1/3, okay? So we may say that while the KdV amplitude profile is governed by this Hastings-McLeod solution of Painlev 2, instead, the Benjamin-Ono amplitude profile is governed by a simpler function. It's just the reciprocal of this Airy function, okay? All right, so what else can we say? Well, we can measure the size of this dispersive edge fluctuation. So if we consider the sort of amplitude of it or the width of it, in both cases, those things are bigger for Benjamin-Ono by like a square root than they are for KdV. So like the fluctuation is epsilon to the third for KdV, but it's epsilon to the 1/6 for Benjamin-Ono. That's the amplitude. The width is epsilon to the 2/3 for KdV. It's epsilon to the 1/3 for Benjamin-Ono. Okay. So that's one difference. Both of these formulas make sense, I guess, at some level, because for KdV, this Hastings-McLeod solution is a global real valued solution of the Painlev 2 equation. And for the Benjamin-Ono, we have this Airy function, which is in the denominator. That seems troublesome, except it's evaluated on this line in the complex plane, right? And that means there are no zeros on that line. The zeros of the Airy function are all on the negative real axis. So this is a function with no zeros at all. So the sort of approximation makes sense. It's also true that as x goes to plus or minus infinity, both of these KdV and Benjamin-Ono formulas match to the asymptotes that are consistent with the sort of, Whittam type theory. So the asymptotic approximation of the U on either side of the dispersive edge. And so for KdV, you see that the amplitude of this Hastings-McLeod has this square root in it, and that's matching this kind of behavior we noted before for the way that the dispersive shockwave behaves near that edge. And for Benjamin-Ono, we have 1 over Airy function, and this Airy function, of course, is going to decay like a 1/4 power. So that's the 1/4 root, just like that, right? So it matches on that side as well. Okay. All right, so what about the other edge? That we call that the soliton edge. So for both of those equations, the dispersive shockwave kind of gets rarefied as you move toward the right edge. And the individual peaks kind of separate out and they look like solitons. So we'll call it the soliton edge. The fastest solitons are going to emerge moving to the right, and they're corresponding to like the most negative eigenvalues of the corresponding inverse scattering transforms. Okay, so what can we say about those? Well, we have the small parameter epsilon, and that somehow helps us to calculate the eigenvalues. And for KdV, you have the Bohr-Sommerfeld quantization rule. And it predicts actually a finite density of the most extreme eigenvalues, the most negative ones, with the fastest moving and biggest solitons. And for Benjamin-Ono, there's a different kind of Weil law. It's called the Matsuno density, and it vanishes actually at the extreme eigenvalues. So that somehow means that there should be fewer solitons near the edge for the Benjamin-Ono equation than there are for the KdV equation. And we might wonder how that sort of stuff is quantified rigorously. So let me try to explain that now. So, okay, so at the soliton edge, what's going on is that the elliptic functions for KdV that model the dispersive shockwave have a hyperbolic degeneration instead, and the elliptic parameter is tending to 1. And so let's set now U plus to be the continuation of the Burger's branch from the right instead. okay, and we'll let U be the KdV solution, and here's the next result of Kleis and Graba. So fix T bigger than the critical time, so there's some positive functions W and gamma, so that this KdV solution is the Berger solution from the right, plus a sum of solitons here, okay, and then there's an error term epsilon log squared 1 over epsilon. Okay, so so here you have to take this coordinate x, or x minus this, sorry, the x coordinate of KdV minus the edge has to be bounded by some multiple of epsilon log 1 over epsilon. And then you have to take the number of terms in this sum, which has always got to be finite, to be big compared to, you know, the constant that's here, but it has to be a finite number. And so then what's in the phase of this soliton, it determines its location, is this gadget. So this is a thin soliton. It's separated from the edge by, well, this amount here that depends on n. So there's like a series of these things as we have terms in the sum, and they're separated by this kind of spacing. And then there's this term, which is smaller. It's got epsilon instead of epsilon log 1 over epsilon. There's a multiple, there's some factor depending on n here, which is, as it happens, the leading coefficient of the nth Hermite polynomial. Okay, so that's the result there. I'll say some more about it in a minute. Okay, what about for the Benjamin-Ono problem? So, well, this x plus is a different curve, but again, we can denote the continuation of the Berger solution from the right at that edge as U plus of t. And now we'll let U denote the Benjamin-Ono solution for some rational U naught initial data. So we'll fix the time bigger than the critical time. XS is X at the soliton edge, US is U at the soliton edge, and so on, like that. So then there are some constants, K S negative and gamma S real, so that the Benjamin-Ono solution is the Berger solution from the right, plus an, okay, infinite sum now of soliton solutions, plus order epsilon to the 1/3. And here, this is holding true as we're close to this edge by epsilon to the 2/3, and the time is also scaled by epsilon to the 2/3. And then here okay, this is the coordinate that's in the soliton. So again, 1 over epsilon times basically distance from the edge, plus, okay, epsilon to the 2/3, constant times Cn is the nth zero of the Airy function. And then there's some order epsilon correction here. Okay, let me now talk about these formulas a little bit. So in both cases, the formula is a sum of identical exact soliton solutions propagating on the background of that Berger's continuation. But for KdV, the spacing of the solitons is proportional to epsilon log 1 over epsilon. That's only a little bit bigger than the actual width of the soliton itself, epsilon. But for Benjamin-Ono, the spacing is epsilon to the 3rd, and that's like huge compared to epsilon by comparison, I guess. So it really explains rigorously this expected rarity of the solitons near the leading edge, okay? But there's more to the story. So for KdV, the solitons that make up the wave train are equally spaced at the leading order. They're clock ticked by n, and n is the index that's in that sum. So that's that term there. But for Benjamin-Ono, they're not at all equally spaced. Instead, they follow the zeros of the Airy function. I really think this is something that people could do experiments on. I mean, those of you in the room who do experiments, you should be able to look at these solitons if you can make some system that simulates, that's modeled by Benjamin-Ono, and you should be able to calculate the zeros of the Airy function by an experiment. An analog computer. Okay. In both cases, there's some kind of effect that the deeper into the shock wave that you go, more dense the soliton train gets. And for KdV, the way this works is that, remember, there was this extra term that was proportional to log of the Hermite constants Hn, and those go to negative infinity faster than minus n. So actually, that's the reason why you can only write the formula with a finite sum of solitons, because actually, if you go too far, the soliton train turns around and they come back out of the dispersive shock wave, which is not what you want. So that's why you have to truncate it. But anyway, it definitely has the effect of pulling them back, and that's the sort of density increase, okay? But for Benjamin-Ono, it's achieved by a different mechanism. It's just the location of the Airy zeros, which we know become more dense as you go further and further out. And that's the thing that determines the sort of density of the dispersive shock wave. Okay, so we can use an infinite sum. All right, so what about near the gradient catastrophe point itself? So that's in fact the same point for both KdV and Benjamin-Ono. It only involves the shock point. So anyway, there's some reason to believe that the dispersive solution here behaves in an even more universal way. So not only should the sort of dispersive shock wave that's growing out of that shock be independent of initial data, but it should also really be independent of the equation. That's at least the belief. So here's a conjecture of Boris de Brovin from 2006. There's some kind of class of dispersive Hamiltonian perturbations of Berger's equation for which the solution near the gradient catastrophe point can be scaled regardless of initial data to match a certain function we'll call d of xt for de Brovin, okay? It's a particular special function that solves the second Painlev one equation. And the conjecture here was suggested by some formal matched asymptotics. And so now I would like to sort of tell you some more about the application. So the special function that shows up in de Brovin's theory, it's defined as the solution of this fourth order ODE in which t is just a parameter, okay? And this is the second equation in the Painlev one hierarchy. The function should be picked out as being this unique smooth solution of this problem that satisfies these cube root asymptotic boundary conditions as x goes to plus or minus infinity. And that solution has been shown to be unique and existing. So, okay. So anyway, as it happens, the KdV equation is a member of de Brovin's universality class, but sadly, the Benjamin-Ono equation is not. So there is a corresponding conjecture about it. And that's this one of Mazuero, Raimondo, and Antunes. So there's some universality class of dispersive Hamiltonian non-local perturbations of Berger's equation for which the solution near the gradient catastrophe point can be scaled independent of initial data to match some other function, capital U of xt, and it was singled out as a particular special function that solves this crazy sort of string equation. Notice the Hilbert transforms here. It's some non-local version of that de Brovin ODE that we looked at earlier. It again should have cube root asymptotics for large x. So in the paper, they couldn't really go further than this. This was the result. So de Brovin's universality conjecture was shown to be true for the KdV equation by, again, Tom Pleiss and Tamara Grava. So here's the gradient catastrophe point. And so that we take coordinates x and t that are localized near the gradient catastrophe point and suitably scale epsilon to the 6/7 for the capital X coordinate, epsilon to the 4/7 for the capital T. Those are fixed. Then the solution of the Cauchy problem satisfies that the KdV solution is this critical value of the Berger solution at the breaking point plus something proportional to epsilon to the 2/7 times the de Brovin function, okay, plus an error term. So that's the formula for KdV. So I want to now tell you the Benjamin-Ono result. So now I'm going to define a function capital U of x and t by an explicit formula. So minus twice the imaginary part of the derivative of log tau, and tau is this Pearcey integral, contour integral in the complex plane, well, you can see where it starts and ends. Okay, so it's like a dog leg contour. Numerics suggest to us that this function tau doesn't vanish anywhere in the complex plane, the real xt plane. So the red and the blue curves here are the levels of the zero levels of the real and imaginary parts. They certainly are not crossing anywhere in the finite plane. We can do asymptotics to prove it for large x and t. Okay, so here's the theorem. So we take a generic rational initial data for Benjamin-Ono. This is the gradient catastrophe point for Berger's equation. And so the solution of Benjamin-Ono is the critical value of Berger's plus epsilon to the quarter times this u function plus an error term. And that holds uniformly on compact sets where this tau is non-vanishing. And so now the coordinates are, okay, x is scaled like epsilon to the 3/4 and t like epsilon to the 1/2. Steepest descent analysis of that Pearcey integral proves that this u function behaves like a cube root as x goes off to plus or minus infinity. Here's some graphs of it for different values of t. Now we haven't managed yet to show that this Pearcey function u, the integral, solves a scaled version of the string equation, but we're hopeful about that. Okay, so the proofs. So this is the slide I didn't want to take out. I know that I know Pana sort of already gave this joke at the very first line of his talk on Monday morning. So I was going to take it out, but I tried this joke 26 years ago in New York City, and it just didn't go over. Nobody understood what I was saying, but that's because I was not in Newcastle, and now I am. Now I am. So we're not going to bring folds to Newcastle. We're not going to apply the inverse scattering transform to this problem. Instead, we're going to use a formula that Patrick Gerard found just last year, 2023. He published a formula for solving the Benjamin-Ono equation in closed form for arbitrary initial beta, like an L2 intersect L infinity. It's amazing, really. So we implement his formula for rational initial conditions U naught. Here's a rational function, poles in the complex plane like that. So I'm going to describe this formula for you. So first, let's recall the Lax-Olenek objective function from shockwave theory. We take this thing, and a derivative of it is just this quantity that involves exactly the initial condition like that. So what we're going to do is analytically continue this H from the real line for Y into the complex C plane, avoiding some branch cuts, like from the poles here. So C0 is going to be a contour that's sort of from the northwest direction of the complex plane to the southeast direction. And then these C1 through CNs are contours that go from the northwest back to the northwest, going around the branch points, okay? So, so now from those contours, we're going to end the Lax-Olenek function. We're going to define two n+1 by n+1 matrices. So A and B, they're just contour integrals. The columns of A and B after the first are identical. It's just the first column that differs. And in the matrix A, we have in the integrand the rational initial condition U naught. In the matrix B, we have 1 here instead, but it's just the same exponential everywhere. So now we have two matrices, and then here's the theorem. So the solution of the Cauchy initial value problem for the Benjamin-Ono equation with rational initial condition U naught is just 2 times the real part of the ratio of the determinant of A over determinant of B. Here's an equivalent kind of tau function type formula, okay? And I want to point out here that not all rational functions U naught are multi-solitons. So this, you may say that this looks like a multi-soliton formula, and you'd be right, because in the multi-soliton case, you can do the integrals by residues here, and it's just an algebraic determinant. But in general, it's not, and this is a much more powerful formula. It includes all kinds of radiation and everything. It's a pretty amazing thing. Okay, so anyway, all of our small dispersion theorems come about the same way. We just do steepest descent, classical steepest descent, not any fancy Riemann-Hilbert stuff, on the contour integrals that make up the matrix elements. So as long as we stay away from the Berger's wave caustics, all the critical points of this exponent function are simple. And that means that the standard formula for simple saddle points is good enough. So we get some approximation we call U0 dispersion of xt epsilon. It's accurate to order epsilon away from the caustic curves. And here's a picture of it for that star-shaped caustic picture. So now you see sort of, this is the approximation. This is accurate everywhere except near the black curves, okay? And our talk today has been about the black curves near this corner down here. So since the exponent function h of z is exactly the same as the Lax-Olenek objective function, what we know is that the Berger's wave caustics in the picture correspond to the confluence of critical points, of real critical points. And so it's necessary now to unfold the confluence to obtain the asymptotics near the curves, that's all. So, so we have colliding saddle points is the point. So for t bigger than t critical, the curves x plus or minus of t, they just signal the coalescence of two simple real saddle points. And the exponent function h has a normal form as a cubic near those collisions, okay? The resulting sort of diffraction catastrophe integrals with this exponent are Airy functions, and that's the reason why the Airy functions are showing up in those formulas. So the pictures for the contours have to look sort of like this in those cases. But near that gradient catastrophe point, instead, 3 points collide, and the normal form now for the exponent is a quartic polynomial, and that explains this Pearcey integral that's showing up in the formulas. Okay, so that's the picture in that case. Okay, well that's it. Here's a pretty picture of some clouds, morning glory clouds in Michigan. Benjamin-Ono's equation is supposed to model those things, so maybe they fly along Airy functions here. Thanks.
Well, just a curiosity about what you said about the Robin conjecture in fact, the Benjamin-Ono does not fall in that class. So I remember this work. I don't remember 2018 by Korteweg and Rossi, where they found the last representation in terms of this last representation. There was, if I remember correctly, a series expansion in the differential polynomial with Bernoulli numbers of the Benjamin-Ono and
I'm not aware of that work, so, yeah. I
it's
mean,
possibly that representation would help find applied problems formulation.
right,
But I'm not 100% sure about any also. Just
okay, yeah, sure. Even
wonder
you
if
can-
you had a look and then it's not the case. Yeah.
That's why we go to conferences.
Okay.
Right. Well, so we don't solve that equation, right? We just, we derive a formula directly from contour integrals. But, of course, one would like to check that, right? We have some thoughts, but we don't have it yet.
Curious about one of the things you told us is that the density of eigenvalues associated with advantages at the top.
Yeah.
Can you break that by relaxing the regularity of the top of the potential?
So the density of eigenvalues for the Benjamin-Ono problem is really simple. What you do is you take the, say you have a positive initial condition. All you do is you just measure the distance between the turning points. And then you plot that, that's it. So if you have like a Lorentzian profile 1/1 plus x squared, the distance between the turning points gives the Marchenko-Pasteur law, for example. And then that vanishes at the extreme edge, and it's got the hard edge of 0. So they actually have most of the eigenvalues are very, very small. And that's also has something to do with the dispersive edge. That's the small amplitude part. Yeah.
Next speaker, let's thank you.